Origins have brought a new and welcome level of roleplay and empire customization to Stellaris. For players that like an additional challenge, the Doomsday Origin offers an excellent balance of enhanced difficulty and story enhancement. Who wouldn't want to act out the fantasy of escaping from a doomed planet to conquer the stars? But is this scenario scientifically plausible? Could a planet be so tectonically unstable that simply tears itself apart? Could the Doomsday Origin really happen? Today, Science in Stellaris tackles the Doomsday Origin. Four and a half billion years ago, the Earth was a molten, hellish planet. Seas of magma flowed freely across its molten surface as meteors rained down from space, superheating the world from the force of their impacts. The thick, unbreathable atmosphere of carbon dioxide and nitrogen was hot enough to melt lead and had only trace amounts of water, and no magnetic field existed to block out the ionizing radiation produced by young, scorching sun. Even the night sky was very different, for Earth had no moon. Thankfully, this Earth, a toxic world where even extremophile bacteria would struggle to survive, is doomed. From out of the distant reaches of the solar system, another planet, Theia, is approaching it on a collision course. Mars-sized Theia formed in the outer solar system where water ice is plentiful. Much like many of the Galilean moons, Theia is mostly made of ice surrounding an inner iron core. And it is about to give Earth its moon and its oceans. Drawn by gravity in a slow, looping spiral, Theia would hit the proto-Earth on its side, and the impact would cause the mutual destruction of both worlds. Out of the debris, a new world and its moon would coalesce, a world with an iron core, a hot layer of magma to power plate tectonics, plentiful water, and an enormous moon to shield the young world from further asteroid impacts and give its new oceans tides. The death of Theia would mean the birth of the Earth as we know it. One plausible way for a doomsday scenario to occur would be for a rogue planet to collide with an inhabited one. Rogue planets that for many different reasons end up escaping the gravitational pull of their parent stars, are likely quite common in the universe, and cosmic interlopers are a proven reality. Just recently, an unusual comet-like body, Oumuamua, detected entering our own solar system from interstellar space on a trajectory that makes it almost impossible to have originated in our own star's Oort cloud. Stars move as they orbit the galaxy's gravitational center, and close passes between stars would be enough for some objects to become freed of their parent star's gravitational boundary. Even planets are not immune from such forces, and a collision between such a planet and another would absolutely destroy both worlds. But this is not how the Doomsday scenario is depicted in Stellaris. The Doom world is shown to simply tear itself apart under the forces of its own plate tectonics. So why spend so much time discussing rogue planets in a discussion about plate tectonics? Because how a planet forms might be the key to how it could potentially end. Let us return to the past. Once more, we are looking at a hellish planet, freshly formed from the accretion of its star's protoplanetary nebulae. And like the Earth, this planet is about to be destroyed by an impact event with another world. But unlike Theia, which brought water, ice, and iron to the early Earth-Moon system, this interloper is a rogue planet and a carbon planet. Carbon planets are theoretical worlds that might form in star systems where oxygen levels are low. Instead of being formed largely from silicon dioxide as our own Earth is, such worlds would have a surface and mantle made of graphite and a small iron core surrounded by diamond. And rather than oceans of water, they would have thick oceans of tar. On carbon planets, plate tectonics will not bring quartz and other siliceous minerals to the surface, but all continental plates will be made of pure diamond. And this planet, strange and alien to us denizens of the solar system, is about to forever change the geology of the new planet that will form from the rubble after two worlds collide. The resulting planet that aggregates from this impact event has aspects of both a carbon planet and a silicon planet, but in some ways it is still Earth-like. It has an iron core that generates magnetic fields, a large gray moon roughly the size of our Luna, but much darker in color due to its graphite content, plate tectonics, and a thick atmosphere. Its oceans are largely a mixture of different tars, but thanks to common impacts, enough water exists on the surface to sustain life as we know it. But where we have mountains formed of granite and other various forms of oxidized silicon, this world has mountains of pure diamond, and beneath this adamantine crust, where Earth has a mantle that is largely a viscous state of silicate rock. This combination planet has two mantles, a lower silicate one buried beneath a thick shell of diamond, and that formula of hot fluid trapped underneath a solid, unyielding exterior is a serious problem for the denizens of this planet. Seismic disturbances on this world are far more infrequent due to the hardness of this crust, but the long intervals between events allows more energy to be stored in fault lines. When tremors do occur, they are far more intense and widespread than the ones we experience on Earth. Mountain forming and plate tectonics is also slower, a hazard for life in its own way. Speciation is less frequent because continental drift is slower, meaning that the planet spends more time in periods where all its land is joined into one continent, reducing the opportunities for new species to diverge to suit novel environments. Finally, major volcanic events are apocalyptic, and unbeknownst to the denizens of this world, an eruption that's brewing deep beneath the surface is about to devastate the entire planet. Most people tend to picture volcanoes as a single cylinder cone spewing lava out of its top, but that view is shaped by our modern experience living in a relatively benign period in Earth's geology. Earth isn't always so pleasant a place to live, for every so often it's beset by a destructive event called a flood basalt eruption. Basalt lava is rich in iron and magnesium, but low in silicates. This makes it runny and fast-flowing, meaning that when enough of it rises at once to the surface, the resulting eruptions tend to be widespread and fast. We can see the results of such an eruption at night by taking a careful look at the moon. Those dark spots, the mare, that cover vast stretches of lunar surface are basalt flows. Earth, too, has had flood basalt episodes. Geologists have identified 11 of them and suspect more will be found over time, and each one has been large enough to cause widespread physical changes to the Earth's geosphere and atmosphere, often in geologically short time spans. Flood basalt episodes can form new mountain ranges, trigger volcanic winters that cause ice ages, turn entire continents into a sea of lava. The list of events associated with such episodes is full of grim-sounding titles: the End Ediacarian event, Late Devonian extinction, the Aptian extinction, and the Permian-Triassic extinction event are just a few examples. That last one has another nickname, the Great Dying, because life on Earth almost died out completely, with some estimates for the number of genera lost at over 80%. It was Earth's deadliest mass extinction to date, and it was caused by the Siberian traps. Traps are named for the Swedish word for stairs, trappa, and refer to the step-like hillsides that basalt flows can form. The Siberian traps, which cover a good chunk of Siberia east of the Ural Mountains, is estimated to have formed from a single ongoing basalt flow that deposits 7 million square kilometers of basalt lava on Earth's surface and lasted nearly 2 million years. Life is resilient and adaptable, but nothing can really prepare a species for the sudden formation of a large igneous province. Once more, we return to our hybrid world. The spacefaring civilization that has risen on this world calls it Kazan, and named themselves the Kahan. A Kahan exogeologist is getting increasingly worried. Their planet, though tectonically active, has always been a rather quiet one. Some members of the exogeology community even fear that the inner core of the world has cooled and that plate tectonics will eventually cease. But recent scans show a worrying increase in heat below the surface of Kazan's sole continent. Fearing a new hotspot is forming deep beneath the diamond crust of their world, the scientists had just published a paper on the new discovery when a series of massive tremors suddenly triggered a deadly tsunami along the shores of the inner sea, where most of Kazan's largest cities are located. Along with the tsunami, several large fissures formed, as enormous splinters of diamond jutted up through the shallow graphite crust of the world. Toxic and deadly gases have been spewing out of these fissures for over 2 months, and constant tremors rock the besieged population centers as a looming refugee crisis drives survivors towards the still-functioning spaceports. A new religious movement claiming that they are entering the end times is growing, and much to his annoyance, the young exogeologist paper is used by this cult as proof that their dark prophecies are true. The leadership of the Yokahan have also taken notice of the scientists' accurate predictions, and now a task force is forming to determine what exactly is stirring deep beneath Kazan's diamond mountains. With practically unlimited resources, the exogeologists and their team have built a probe capable of descending deep into the very mantle of their planet. The probe descends using a powerful laser drill system, beaming data back to the surface that is detected with the latest in gravitic sensors. The exogeologist shivers in fear at the resulting data as it streams in. The newly formed fault line has weakened Kazan's crust, and up through the cracks in the diamond mantle, a veritable ocean of magma is now rising. A volume of lava nearly 4 million kilometers cubed is about to burst through to Kazan's surface. Such an eruption would threaten the entire continent. Wondering how they will break the news to their world, the scientist was caught unawares when a shockwave like a hurricane suddenly flattened every building for kilometers around, bodily fluids flowing out of their ear canals. The now deaf scientists looked toward the horizon with double vision. Far, far in the distance, a bright plume of lava, already kilometers tall, is still rising, and above it, a diamond as big as a mountain is exiting Kazan's atmosphere. Bolide, thinks the exogeologist idly, before dying to the newly formed blood clot that the sound of a world exploding made when it concussed their brain. Bolides are a general term for large-scale impactor events. Most bolides are meteors, but some can be caused by so-called volcanic bombs. Volcanic bombs operate under the exact same principles as a potato gun. Superheated gases get stuck behind a solid obstacle, build up pressure, then force the obstacle out of the way with that pressure. With truly gargantuan volcanoes like basalt flows, truly gargantuan volcanic bombs can be formed, and a large enough volcanic bomb is potentially no less devastating than the more traditional meteor impact. A falling rock is a falling rock, whether it comes from outer space or got launched there by a powerful volcanic eruption. On a hybrid world rich in both carbon and silicon, it is possible that very large bolides might form out of pure diamond, accelerated into a degrading orbit by an explosion of built-up magma. Such bolides might be enough to wipe out all life on such a planet. A supermassive bolide the size of a mountain would have enough impact energy to turn a continent into molten slag, triggering Doomsday for an entire world.